and today I will attempt to teach high school geometry. As you might know, because, well, you might, or if you look at my channel and subscribe, please subscribe. If you look at my channel and subscribe and like, hopefully, actually, you don't have to like the videos. No one cares about likes, okay? Just subscribe. I don't care about like. You don't have to like the video. I don't care. And I don't care if you comment, but if you comment, that'd be nice. I like comments. At least good comments, at least. I don't care about likes at all, so do whatever you want. So anyway, what I'm saying is that you might know that I teach real analysis. Now I'm starting another part, more math. So this one is based on my AOPS textbook called Introduction to Geometry. So we're going to cover, let's see what we're going to cover. We're going to cover 1.1 to 2.8. This is going to be quite a lot of lessons we're covering because there's not much in these first two chapters. So it's going to talk about angles. So the first lecture is always about angles and lines. So we'll get to very interesting stuff later on. So what's in a name? That's the name of the first chapter. And they say why names are super important. Now, here are some things, like some parts of geometry. A point, 0 dimensions, it's a point. You'd have nothing to do. If you lived on a point, you'd be awfully bored. That's the exact quote. No up, down, no left and right, just a singular point. Now, we extend into 1 dimension by connecting 2 points. So we have this 1 point, and now we have connecting 2 points, A and B. This is a line segment, and this is 1 dimension. You can go left to right, but you can't go up. Actually, this is 2 dimension. Like, if you look at it carefully, you can see some height in this. But, and by the way, this is also 2-dimensional. Everything on this thing is going to be 2-dimensional, but just assume it has no other dimensions to it. And this, just assume there's no height to it, just length. Now you have a line segment, and apparently in the book they actually measure it. I don't have a ruler with me because I wasn't exactly ready to measure it. So yeah, this is a line segment. And between a line, there are infinitely many points which can be placed on the line. Say here, here, here. But okay, the middle point, let's assume this is right in the middle, though it might not be because I didn't measure it. Let's assume this is the middle point because it kind of looks like it is. And the middle point is called the midpoint. I'm going to call it M because midpoint M. And here's just a diagram. I'm literally copying all the diagrams word for word. So yeah. This is if you have the literal book, you can literally see what I'm doing here. I mean, this book is $60, so this is a pretty good deal that you're getting this all for free on YouTube. YouTube's pretty nice. So, what do these 2 lines mean? These means that these are the same length. Again, these might not be the same length. I didn't use a ruler. They used a ruler. They definitely did use a ruler. They even said they used a ruler. We didn't use a ruler. We just assume these are the 2. Sometimes with the figure, there might not be to scale. That's what I mean. This is not drawn to scale. In fact, not drawn. NTDS, NDTS, NDTS. Assume that it's not drawn to scale. Now say you're living on point A, but you just don't want to go left to B. You're going to keep going from B. let's. And you want to keep going infinitely forever. So this is called array, as most of you guys probably know. Oh yeah, and the line segment A to B is, I forgot to put this earlier, AB is a line segment, and now it's A, B, but instead of just this, it's also going to be an arrow pointing in the B direction. And say you want to go to both sides. Again, these are one-dimensional figures. Even the line is going to be one-dimensional. If you want to go to both sides, A and B, A, B, M. They didn't draw M, so I'm finally changing things. So, line AB. Now, sometimes we often leave off the little arrows in the diagrams, but I try to say it's a line, not a line segment. Many of the times you have to assume it's a line. But like for now, we should just keep this AB, line AB, both directions. Not that deep, right? Okay, so now let's show you what collinear and concurrent means. So, if there are 3 points, 3 or more points are on the same line, the points are collinear. So like these points are collinear to each other, same line. Points on the same line, collinear. And kind of the opposite, instead of 3 points, it's 3 lines all at one point, is concurrent. These lines are concurrent to this point, which I'm going to call W, because it's a W point. Gen Alpha. It means win. Whatever. The W point connects 3 lines or more. It can be more. We just put 3. And then in this textbook, they're gonna, in chapter 14 in this textbook, we're gonna add a 3rd dimension, but we're not gonna get to that point until a really long time. I mean, like, I'm actually doing this class currently, and we've passed 14. We're on 14 actually. We're doing 3-dimensional. So yeah, 3 dimensions. Yeah. So now, the next chapter is about circles, but since we learned all this stuff in the chapter 10? Is it chapter 10? Oh no, not chapter 10. Not chapter 10. Chapter 11, circles. Chapter 11, circles. Yeah, we're not going to talk about that right now. And the construction thing, we can't do that on the whiteboard, so if you have the textbook, you can look at it. And they talk about the golden ratio, which, if you want to know, it looks like this. Oh, apparently this equals to 1 plus the square root of 5 divided by 2, if you want to know. So this is the golden ratio. Okay, anyway, angles. When 2 rays share an origin, they form an angle. Not too bad of a definition. 2 rays, an angle. Of course, 2 intersecting lines make an angle as well. Angle, 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 angle. And there's actually a theorem for that, but okay. So, over here they have the intersecting lines. Again, these are 2 lines, but like it's fine if they're segments as well. A, B, C, A, B, and C, D at the point P. So APD, APC, DPB, and CPB. Now, cool thing is, which is very gonna come later, intersecting line theorem. These and these are the same. These and these are the same. Okay. Measuring angles, use a protractor. We're not gonna use a protractor, though they have a very sneaky thing on problem 2.1. like in the class, they're like, hey, you can't just trust how it looks. Though like most of the time, you can't. It's drawn off the scale, or the angles just trick you, and protractors are very unhelpful. What they mean by that is that they were joking around and they said that this angle has a measure of 89.999999 degrees. 9999. 89.9999 degrees. So close to 90. But most of the time in problems they'll actually mention it or you'll calculate it. Just don't judge it off of looks. That's the point. So this is problem 2.6. What is AOB? OB. And you guys probably know this is a straight angle. What is straight angles? What are the measures of straight angles? What's this? 180. Yeah, you guessed it so correctly. Oh god, it's raining a lot outside. Well, anyway, I don't care about the rain outside. I do care about like AOB is 180. So, now that we know this is 180, we'll look at supplementary angles. Problem 2.7. Y XZ is 55 degrees. See, we gave it to you. And this is a straight line. Straight line. Yeah, see, it says lines in the thing, and they didn't put line symbols. So meter X. So I don't. Fine, I'll just put them there for the sake of it. But this is 55 degrees, and this is a straight line, okay? I'll promise you this is a straight line. What is this? And don't try to use a protractor. It's not going to help you. The way we can find this out is doing 180 minus 55. And you're like, how? And I told you it's a straight line. I mean, it doesn't look super straight. Because my drawing skills are pretty bad, but oh wow, that noise you heard outside, that's rain. I'm gonna check it out for a second, but it's 125 degrees. If you got that, let me check. Yes, 125 degrees. So, problem 2.8. Yep, 2.8. So, like, remember the intersecting theorem? Well, think of how to do this. Well, first you can do 180 minus 72, and then take that result. Oh shoot, I already put the answer. Oh god. Give me a second. Oh god, it's completely wet outside now. In like a matter of 2 minutes, it's completely wet. But how is it 72? What you're hearing right now is a crazy amount of rain outside. Oh god. That looks concerning. Okay, anyway. So, I've been talking about rain for the past 2 minutes, sorry. So first we do this. This is 8. This is nothing. This is 108, right? And what's 180 minus 108? 72. But how? How can you prove this algebraically? It's two supplementary angles. Well, technically, here's how it works. If two angles are supplementary to the same angle, then they're definitely the same angle. That's like common sense. But like, let's see like this, like 180 minus 1 minus x. Let's do 180 minus this. Well, if we take everything out, it's 180 minus 180 plus x. So it's x. You know, I'm keeping the window open. I like the sound of rain. Okay, it's not even raining as much. It's fine now. So we just proved that the opposite angles are equal. This is the intersecting line theorem, which I was talking about earlier. Two lines, this doesn't look super straight, but the two intersecting lines, then the opposite angles are equal. And we actually just did 2.9 in this, so we're not doing 2.9. We proved it. And now we extend this thing to parallel lines. Now we won't do the problems, but I will tell you. This is called a transversal. This line cuts to two parallel lines. These lines don't look parallel, probably because in reality they aren't. But assume they are parallel. Because my drawings are so bad, how am I supposed to teach geometry? I suck at geometry and drawing, so this is the best parallel lines I can do. And we have angle x. Well, this is also angle x, and let's call this angle y. An angle y. If these are parallel lines, and this is going to be one straight transversal, these are parallel, then this is the theorem, and then you won't have to prove it today, but same thing is replicated on the bottom. Now I won't actually memorize the names, but here, I'll give them different names. I'll just tell you because of how annoying the name. I don't like memorizing this stuff. It's just no reason. It's just copied on the same thing. I don't care about names anymore. Alternate interior, exterior. You'll see, the names suck. So A and E are corresponding angles. They're equal. Their names are not important. So the names are not such a big deal. So if you want to know though, A and E are corresponding angles. D and F are alternate interior angles. A and G are alternate exterior angles. C and F are the same size angles. B and G are same side exterior angles. And B and G aren't exactly equal. C and F aren't equal. A and G are equal. D and F are equal. And A and E are equal. Don't memorize these names. Well, I don't suggest you to. Memorize them. If you're crazy, if you're like one of those people who memorize 2,000 digits of pi, memorize this. Okay. So this is parallel lines. This is the theorem. Now, angles in a triangle. Now in this one, problem 2.15, they just ask you to measure the angles. And we won't do that, so we'll just say that the sum of the angles is always 180. You guys probably already know this. The sum of the angles in a triangle is always 180. So you saw right in triangle we want to prove. So here's the very nice triangle. I'm going to prove ABC plus ACB plus BAC is 180. We don't know a whole lot about angles. Yep, we don't. So we use a line. because 180 line. So here, these are alternate something, alternate interiors, whatever. This is parallel lines again. Comes super useful. Parallel line thingy. It is so useful. These are parallel line only. So this is super useful. That's what my point has been trying to be. So these are parallel lines. So XAB. Oh yeah, sorry, I didn't define X or Y. So in this situation, XAB plus CAB plus CAY is 180, right? Because straight line. Over here, you see the straight line, right? Well, we keep the CAB, but XAB, what is that equal to? ABC. What is CAY equal to? YAC. Not Y, ACB. ACB. So all of this checks out. All of these angles add up to 180. That's the proof. It's a very fun proof to do this one. It's so easy and fun. Other proofs are kind of weird. So close the book and try to recreate this proof on your own. Okay, so here, line, here, this is this. Oh yeah, by the way, these are equal angles. We put a weird thing to here. Here, this is 180. This 180. Yep, fun. I should memorize this proof. You should know this proof. It's a very fun proof. So we'll do exercise 2.5.1. Oh yeah, we'll also do 2.5.2. So, two angles in a triangle have measures 30 degrees and 57 degrees. What is the measure of the third angle? So simple, we just 87. 180 minus 87. Well, it's actually 93 because it's... So it's 93. Now 2.5.2. 1, 2, 3. So if it's in ratio 1, so the angles in a triangle in a ratio 1, 2, 3. What are the measures of the angle? So this is 1x plus 2x plus 3x. This is 6x equals to 180. Now if you divide by 6, it's x equals to 30. And then it's 30, 60, 90. Oh shoot, this is the 30, 60, 90 triangle. This is a very useful right triangle. Okay, very useful right triangle, but okay, so 2. So ZYP, this problem actually, did they already talk about the remote angle theorem? Because I missed over that part, I skimmed over it. But I'll introduce it to it since we got onto this problem. So 52, 58. This is the diagram. Solve for ZYP. So, the remote angle theorem is basically common sense. So 180 minus x plus y plus y. This is there. So 180 minus x minus y. This is the angle, and this is 180 minus 180 minus x plus y. So this is x plus y, basically. And it makes sense because the complement the sum of these is complement to the same angle. This is complement to this angle, and the sum of this is complement to this angle because triangle. So this is x plus y, so we can immediately solve for this instead of going through all the trouble. This is 110. So 110 plus 29 is 139. And if we subtract 180 from that, 41. It's 41. Yep, 41. So it's 41 degrees. 2.5.4. One of the angles in a triangle is a right angle. Two of the other two are complementary. Oh yeah, I didn't talk about complementary, supplementary. So basically, supplementary is when there are two angles which add up to 180. As you can see in this figure, this and this are supplementary. And in this figure, assume this is a right triangle. These two angles are complementary if they add up to 90 degrees. Supplement, complement, supplement, complement. 180, 90. So basically what this problem is saying is one of the angles is a right triangle. In a triangle is a right triangle. Show that the other two are complementary. Well, it's a triangle, so 180 minus 90 is 90. So it's 90. The sum of the other two angles is 90. That's the definition of being a complementary. Lucy, what do you know about triangles? Find a different solution to problem 2.14. What? What's 2.14? Oh yeah, we're not doing that. It's fine. So exterior angles or outer angles. Oh, this is the remote angle theorem. Yep, it came up. Exterior angles. So basically, this is an exterior angle to the triangle. An exterior angle of a triangle is equal to the sum of the remote interior angles. So, say we have this, then, no, say, this is for any figure anyway, but let's extend. Okay, no, that didn't work. Let's take a nice triangle. Betty Crockett. So exterior angles add up to 360. So apparently these up all add up to 360. Anyway, so exterior angles of a triangle add up to 360. Oh, yeah, that was the problem which just came up. Find x plus y plus z. It's 360. That's 2.2.3 anyway. 2.23, not 2.2.3. It's 2.23. X plus y plus z, or the exterior angles, add up to 180. I suggest you get the book because sometimes I really just don't say the problem. I don't even show the figures. So here's the figure. See, as you can see, already one exterior, second exterior, and third exterior. These add up to 180. 360. Okay, so this is kind of the opposite of the parallel line theorem. Say that these are 40. If these are 40 degrees, this and this are parallel, and this is a transversal. That's 2.24. A. So, in the diagram, what can you say about lines K and M? Well, they're parallel. So, actually, it's called, this is how they put parallel. So, these are parallel lines. And over here, I'm gonna give you a figure, which is wrong. And the reason it's wrong, this is a wrong figure. This is very misleading. Oh, it's not 46, this is 40. It has to be 40. Okay, so this is wrong. Why? Because these are the same angles and these must be parallel. These must be parallel. But these meet. They can't meet. It's impossible to meet. This is not a triangle. This is not a figure. This doesn't exist. Okay. Even in my math class one time, in like my school math class, they gave a triangle which couldn't exist. I'm like, hey, this triangle can't exist. You find out how it can't exist, but I'm like, it can't exist. It's not possible. Yeah, things sometimes can't be possible. The second figure isn't valid. So, this is basically going to be the end of our lecture. Remote angle theorem. An exterior angle of a triangle is equal to the sum of its remote interior angles. And the sum of angles in a triangle is 180 are both very useful tools to help solve problems. And also from chapter 1. Remember that. Remember your stuff from chapter 1. So anyway, we're done with the first lecture. Actually not lecture, but first class. So bye.